Today I wanted to talk to you about scaling 3D graphics on the web, which I think is a pretty interesting topic. And I'm Giulio Zausa. I don't want to spend any time to answer myself, but that doesn't matter much. But I wanted to first of all start by highlighting a very important date. And it's that WebGL, that is a technology that allows us to create 3D experiences on the web, has been released in 2011. It's like 11 years ago. And a lot of time passes, a lot of stuff happened. And I think it's interesting to see how there has been a transition moment. Because initially, when WebGL came out, it was some kind of, ooh, you can make some cool demos on the web, and it stopped there. Mostly because there was not a lot of browser support initially, and people didn't actually know how to program it. There was no libraries, no ecosystem. So a lot of people just did the classic demos and stuff, and the thing stopped there. But after a while, some companies saw this opportunity and said that, well, but actually I can use that for my website in a way that benefits my business. Imagine, for example, a company that sells furniture and want to show you in 3D how your room is going to look before selling you actually the furniture. And in 2016, 2015, this exploded in a certain way, so that a lot of websites like IKEA gave those kind of experiences on the web. But it was almost like a gimmick, it was a box of the website that was not the entire website was 3D aware. It was an experience that some website offered. Nowadays, instead, we open Google Maps, we click the 3D button, and everybody is able to see every part of the wall in 3D. Nobody thinks about it, but that's actually done with a lot of WebGL code that does a lot of very interesting stuff. And nowadays we take this for granted. Yeah, 3D on the browser, whatever, that's easy. No, it's not. That there is a lot of work that is behind this. And but also, we're not necessarily talking about stuff that is just 3D. I'm not sure if anybody of you knows Figma. It's an online editor that works between Sketch and Illustrator to do vector graphics and mock-up prototyping on the web. And that's entirely done with the WebGL. Every part that you see here, it's all rendered with the GPU, and they have a giant, almost a game engine written in C++ to be able to handle that. And so, since now 3D graphics on the web, it's used in a lot of websites, and we don't even know that it's there. Can we say that 3D graphics nowadays, it's a commodity, it's something that we take for granted and it's easy to make? Not really. And it's certainly easy, because nowadays we have a lot of tooling and ecosystem. And I might say that the most important tooling and library that we use nowadays, it's THREE.js. That is a very big library that allows you to use THREE.js, that use WebGL and create 3D experiences in a way that is way easier compared to what it was before, where you had to write shader code, the GLSL manually. And nowadays, other than that, we also have integrations with React that recently from 2018, 2019 exploded. And I'm talking about a library that some of you might already heard, called React Fiber, that allows you to generate the entire 3D experiences on the web in the same way that you would create a React application, in a declarative way and with very few lines of code. And a lot of people built a lot of interesting stuff with this library. And that's because it offers a giant ecosystem of composable parts. I don't have to reinvent the wheel every time and build my own cameras and whatever. I have libraries that allows me to do stuff faster. Post-processing, a Flexbox engine, physics, accessibility. For example, there is this beautiful library called THREE that provides you with, I think, like 200 3D components that you can just add on your application and it will work out of the box. So creating a 3D experiences nowadays, it's definitely easier than it was before. And of course, this meant that everybody took the opportunity and did talks about it, like how to create your 3D model and include it in your own web page. A lot of people talked about this because it's a very interesting topic, and it's unfortunate that a lot of people, though, did only the hello world and stopped where the actual difficult stuff started. But we're talking about that nowadays it's easier to do this. How easier? You can see this example here, and it's very cool because you can see that the materials is pretty complicated. This is on our web page. You can see all the reflections and the fact that when they are close together, they have a shadow. And when I move the mouse around, there is a physics engine that simulates those spheres that collide with each other. And how many lines of code do you think that this example is? Or rough estimate, if anybody has any...
30.
30? 60, closer. And so, it's I create a canvas, I add some lights, I add physics, and I add some components, done, whatever. That's because it's like the meme in Python, import machine learning, it is basically translated to JavaScript. But another example, Minecraft, 180 lines of code. But of course, this example with Minecraft misses a lot of what is the real complexity. And we will go over what is the real complexity that is hidden a bit later. And so, a lot of cool demos we have seen. So does this mean that now I can build my Figma, Google Maps, or data-intensive app with data visualization and whatever in a very few lines of code? No. It's not happening. You can have as many libraries as you want, but you always have to think about what is the problem that you are solving. For example, there is a beautiful library built on THREE.js that specialized on showing 3D maps, like the one that is in Google Maps, but done open source. And it supports a lot of different formats, and you can move all around the globe, and it always stays with good performance. And so, how many lines of code is this library? 10,000. That's a lot going on if you want to build something that is real, that works with a lot of data. And that's because it's trying to solve a lot of different challenges. It needs to efficiently load and unload lots of data on the fly. It needs to stream pieces of maps from the web. It needs to handle the level of details so that you can zoom out and zoom in and automatically load the lower and higher resolution version. And also, if you want to support the mouse, you have to do Raycasting that is super fast. And that's almost a point in which you don't need to buy JS books anymore, and you need to buy a book like this. Because we have, when we're building something like that, we're almost building a game engine, because that's what the 3D games have to face when they want to build for example, open world games. We need to handle a lot of stuff that the stuff that is distant from me is lower resolution, the stuff that is nearer to me is higher resolution, and we have to code that manually because it's very, very hard to code something like that in a library because it's so application specific that you have to start from what is your data. And back to Figma. How does, for example, Figma manages to do something like that? Because you may think, yeah, okay, it's just some 2D shapes, but actually there is a lot of complexity going on. And I think that one very cool thing, one very cool way that you can see how Figma works internally, if you throttle your computer, like your GPU and CPU, and try to zoom in, you can see that, for example, we zoom in And you see that it's pixelated and it slowly loads in. Then I zoom out, I go into another place, I zoom in, and then it dynamically increases the resolution. That's because to be Figma to be possible, they had to write almost a game engine that is able to divide the entire canvas into squares and render them at different resolution with least recently used cache. Like, there is a lot of stuff going on if you actually want to make something this complex. And they spent years developing a C++ based WebAssembly engine to do that. It's a lot. It's a lot. So we can see that even though 3D is easier nowadays, it's still a data problem. Because we need efficient data structures, efficient algorithms. We need indexes to represent our data so that we can find around it faster. And we need to be able maybe to support streaming from the web, because we can't download everything at once. And we also need to do a lot of preprocessing, because everything that we preprocess in advance, it's something that the client computer won't need to do in the end. So that's a bit the state of how is the 3D graphics nowadays. We have a lot of stuff that is simpler if you want to build something cool for your portfolio page, but when you go into actual problems with a lot of data, such as an entire editor or showing maps or showing data visualization, it gets complex. So today I wanted to talk about a bit a real-world scenario of a 3D graphics application and what it took to be built. So that's a bit unrelated, but those are printed circuit boards. And those are used in electronics to connect different components together and make a circuit. And you can see that this is something that has been designed in a computer, in a software that is specifically designed to do so. And the software that we use nowadays to do that, we have a lot of different software such as KiCad, Altium, Eagle. And they're very complicated piece of CAD software that needs to support extremely complicated traces and components. You see that there is a lot going on here. And we also want a 3D representation so that we can have like a preview of what we are building before actually manufacturing it. And the problem with those tools is that they are complicated, they are old. You see that they basically have an interface that you would expect from Word 2002, and they are client-based. So with other people, we asked ourselves, what if we had a way of doing that in a more modern way, like on a browser, on the web, like Figma does? And that's why we are building this tool that the company in which I'm working on, called Flux, that is a browser-based end-to-end electronic design tool. Imagine like Figma, but a CAD tool for design and printed circuit boards. And like I said before, designing something like Figma, it's really complicated because of a lot of data that you have to handle. And this is even worse, actually. And you can see that, for example, we have a view that is very similar to Figma. We have a lot of 2D structures that we are able to move around and add new components, draw lines. And we are also able to view our board in 3D. This is on a browser, so that we can see what we're building and have a clear an approximation of what will come out of the factory. And so, what are the challenges that we faced and something that we are still struggling with? We need to support up to 10,000 electronic parts, like on the same board. Every electronic part can be made up by up to 100, 200 2D shapes. And the entire document can be viewed at once, so I can zoom out and see everything like in an open world video game. And also we have a 3D view. It means that we want to be able to see the thing not only in 2D, but also in 3D. And this means that we can't keep a cache of what you already rendered, because the moment that you rotate the camera, everything gets invalidated, so we can't use the same tricks that Figma uses. Real-time speed peaking means that if I click on something, I don't want to wait 3 seconds before the element selects and the menu appears. And everything needs to run at 60 FPS on medium end hardware around the 2018's era laptops. You see that this is a lot, especially to be run in a browser. And oh no, I put it in the wrong folder. I'm sorry. Skip this one. So we are using THREE.js and React Fiber, and we are using some methodologies, I will say, to tackle our performance problem, and that's what I wanted to tell you today. Like, doing 3D stuff is hard, but if you follow some methodologies, then you can ensure that at least you can control what is happening. One of those, it's using the profiler in Google Chrome a lot. That is a very powerful tool that allows you to record what is happening inside your browser and see, like in a single frame, what's taking the most time. Imagine, for example, that you want your application to run at 60 frames per second. This means that if you do a division, it means that between 2 frames you have exactly 16 milliseconds to do all your stuff. So you need to start profiling and see every frame what is happening, and see, for example, that there are some things that takes a lot of time and they are not really needed, and you have to always start optimizing those first, because you need to stay inside the 16 milliseconds budget that you have. And some of those are unavoidable. For example, the GPU communication, that's literally the hardware talking with each other. But some of those, it's what we worked on optimizing the most. Another methodology that we used is using faster data structures. This means that sometimes a lot of stuff is done with simply lists that have linear time search. And sometimes it's the laziest and the easiest option when you're development. But at a certain point you can't do that anymore, and you have to use more expensive, not more expensive, but more complicated data structures, such as binary or R trees. And that's what we're using internally. And another very cool thing that you have to be careful is doing asynchronous self and time slicing. This means that sometimes you may have an operation that takes 3 seconds to be applied. That's unacceptable from a user experience point of view, because imagine that you press a button and your entire browser stays locked for 3 seconds and you're unable to interact with it. That's very bad for user experience. So what we are doing is that we are splitting our operations in chunks of work, so that we can schedule them asynchronously, and the browser has a way to react to the changes in the meantime. And this is basically something that we get for free with React 18, because it's already supported internally. But it's something that if you have some custom admins that are running, you need to do that manually. But there are specific libraries to do so. And the last and most important methodology that you need to follow when building 3D stuff is that you need to know what a GPU is and what it's doing. Because GPUs are extremely powerful, and most of the time, if you see that your rendering is low, it's your fault that the CPU is taking all the priority. Because a lot of time there are a lot of ways of doing stuff faster if you move it to the GPU instead of doing it programmatically on the CPU. And I wanted to give an example of this. As I said, if you communicate between the CPU and the GPU, there is always a bottleneck, because they literally communicate, they're distant from each other, at least on a computer. And they need to communicate in a shared bus that is PCI Express. So every time that you ask the GPU to do something, it's taking a bit of time. You need to group your calls to the GPU as much as possible. And the way that you do that it's by using a technology called instancing. Imagine that you want to display 10,000 instances of a 3D sphere. What you would do is that a for loop in which for each sphere you ask the GPU, hey, draw me this, draw me this. And it creates some sort of waterfall between the CPU and the GPU in which you're wasting a lot of time because the CPU is constantly waiting for the GPU to finish and every time it doesn't have time to synchronize, so you're wasting a lot. So you see that, for example, if you render those 10,000 elements, you are getting a very bad frame per second. This is 33 on a MacBook Pro with 10 cores, so on your user hardware it's surely going to be slower. And but as I said, there is a very good way of optimizing this. Instead of doing a for loop every time asking the GPU to do something, you can just say, hey GPU, draw me 10,000 elements, instead of doing it continuously. And you ask the GPU to do multiple stuff at once, and in this way we can easily achieve more than 120 FPS without too much effort. So this is a very good way of, if you have a lot of stuff that is being drawn, to optimize it and spend a lot of less time when drawing the same thing over and over. And the cool thing about the GPU is that you can customize how they work. And so, for example, in Flux, to be more efficient, we encoded the logic for drawing 2D shapes, such as rectangles and lines and circles, directly on the GPU. We are, instead of generating the geometry on the CPU, we are just telling the GPU that we want some rectangles with some positions, color, border radius, and size. And what we end up with is that we are able to support a lot of rectangles. You see that here we have a lot of rectangles with different size and border radius. And if we zoom out, you see that actually there are quite a few. That's not all, we have more. You see that there's like 12,600,000 triangles at 120 FPS. And that's because GPUs are amazing. They're very powerful. And most of the times, if they're slow, it's because you coded it badly and you did more stuff on the CPU that you were supposed to. Yeah, that's a lot of rectangle. Yeah, that's a bit a demo of what we're working with. And this is just an overview, I won't go into depth for this, but to actually use this with React, we built a context abstraction called HyperInstancer. I worked with this one, with which you can just spawn React components for your 2D models, and they will be automatically grouped together if they are similar and grouped into a single core to the GPU, so that we won't do this for loop, but we are merging the data as much as possible before doing the calls. And that's some of the cool abstraction that you can build when you are working at lower level with React and THREE.js. And yeah. Another problem that I want to spend very little time to talk about it, but it's all, I think it's also interesting. It's text rendering. Because on the browser you can just add the text, whatever HTML, the browser handles it, and you don't have to worry about it. In WebGL, no, there is no native support for text, and if you want to do it, you have to do it yourself with shaders, with geometry. And the simple ways to do it is like generating geometry for it. So for example, we converted this A shape into a set of triangles, which becomes basically 51 vertices for each letter. Imagine that you want to display 10,000 elements, that's 51, no, it's 5, I can't do math, but you can calculate how many vertices are those. And the GPU is going to cry with that, because that's too complex. And so, one very easy optimization that we always did since the beginning of video games is approximate it with rectangles, every letter, that are 2 triangles, and apply a texture to it. Apply an image on top of it, so that you end up with just 2 triangles instead of 17. And that's a giant optimization, But you can also see the problem is that if you have a font defined as an image, when you zoom in, it's going to be pixelated. It's going to look like a video games from the 90s. We don't want that in our application. So this is a thing that came out some weeks ago with a very cool method called the multi-channel sign distance field that is like from a computer graphics paper from some year ago, in which we don't codify the fonts as the image on its own, but as the distance from the shape to that pixel, so that we are able to interpolate it and generate text that has a much higher quality. And this is a small example. You see that we have a lot of text going on, and it always stays crisp at every resolution. And it's basically drawn with a single call to the GPU because everything is grouped together. Yeah, that's how we are handling text. Last thing, I promise the last. Raycasting. It's a very interesting problem. That this means that when you click on an XY position on the screen, we want that element to be selected. So, how do we determine which element we clicked on? Because this is not handled by the browser. This is just a canvas. We just have the XY position. The naive way of doing it, that is also what React Fiber does internally, is that we iterate for each element and we check the intersection with each one. That's the brute force approach. And it's ON and intersext. We're basically checking with every polygon that is here. This needs to be executed in real time, because if you move the mouse around, that's running for everything. That is not going to scale. That is the default that the React Fiber offers, and it's extremely slow that we figured out that it took like 90% of our rendering time. So, if you have something a search problem that is O of n, how do you optimize it if you have something that is in 2D? Use trees. That's what video games always have done, and there is an entire book dedicated to this matter. The idea is that you represent your scene, your data into a tree structure, so that then when you want to search for what is there at a certain XY coordinates, you can simply explore the tree and directly find in much less time. And with this we basically gain 90% performance for free. And this is something that your browser already does, because when you click on a button or on a text field or something on the browser is doing that under the hood. But if you're coding something with WebGL, the browser is like, whatever, implement your own stuff. And so basically that's how you have to do it if you want to be performant. And yeah, if you don't want to code trees, that's fine. Internally, we use that library called Airbush that implements an Air tree, which is like extremely performant. It uses already all the performant algorithms under the hood, so you don't have to implement everything from scratch. And last thing with disclaimer, but that's a big topic, is that we're using React, and React it's very optimized, it's very fast, but it will become a bottleneck if you are not careful enough and if you don't know what you're doing. Because it's very easy to move the state of your document up, and every single time that you move something, everything down your tree renders, and that's extremely slow, so you have to use a lot of tricks with state management to have it fast. But I think that's basically an subject for another talk, because probably already talked for a lot. How much did it took?
Half an hour.
Really?
Yeah.
Only?
Did you plan for 2 hours?
Continue, please.
Yeah, so I can add something. I had a slide before. So I said that what we are using internally is called React Fiber. And React Fiber has a lot of community around, a lot of libraries. And it's very cool because it has a very nicely written documentation. And it specifically talks the documentation about do and don'ts in React. Because every time that you perform a React update, it's going to do a lot of operation under the hood. And if you want to do some sort of animation, imagine that you click and drag something and it follows your mouse, you can't do that inside React. So what they suggest is that you should avoid set-stating loops, you should avoid set-stating fast events. So there is a lot of tricks that they really give you to make your application faster. And a cool thing is that we applied all of those tricks like religiously, and still they're not enough, because still we had to rewrite the Raycaster, we had to efficiently load and unload the represent the entire scene as a tree. So yeah, if you want to do something like that, there are some ways, like the one that I described here, but I will say that they are almost on your own. You need to take what is your data, what is your problem that you're trying to solve, and really think like, what is the faster way that I can represent this so that I don't need to redo a lot of stuff over and over, and how can I fake also? Because a lot of time when you do computer graphics, and this is something that we always did in video games, we fake a lot of stuff. Imagine, for example, that you the example that I showed previously with the video game. Video games internally, they really do this thing that you see that the mountains up here look like high resolution, but actually they're like some polygons. They are very rough, and that's because you have to know that the user won't notice something. You have to be careful about what is the user going to notice and what really doesn't matter, and optimize for those things. And yeah, that's thing. Yeah. Yes, I wanted to have it.
Can you go back to the PCB board 3D thing so I can take a picture with you pointing at it?
That's an image that I took for Twitter because we were doing our weekly meeting and it was like, wow, that looks good. Here.
Yeah, exactly that.
We are.
And point at it because you're a professional.
The laser.
And smile.
Thanks, really cool talk. Thank you.
Thank you.
So at this point, is there other questions?
Yeah. Are you using WebGPU or WebAssembly for performance?
Okay.
Assembly?
That's very cool because WebGPU, we wish it's not here. Like if you look at WebGPU, it basically doesn't work. You have to download a specific version of Chrome Canary and enable a flag when you start Chrome. And still the API is not stable, so every example that you're going to run is going to crash. I mean, we wish we would use WebGPU, but it's still not there. And also the problem with WebGPU is that it unlocks some advanced things. For example, in WebGL, you can program the GPU using GLSL, and you can probably basically program what it's doing with every pixel and with every vertex. It's called vertex shader and fragment shader. With WebGPU, instead, you go further, and you are even able to customize how the different stages of the rendering process work. But the problem is that even if we employed it, it will probably going to be slower because we figured out that 95% of the optimization that we can do today are actually in the CPU. There are more like data problems there, for example, that we are using React too much to apply the transformations, or already with WebGL you can go 99% of the road when you want to build a product like that. For example, Figma, they were using WebGL, and I don't think that Figma is slow. WebGPU makes sense in some cases. Imagine that you want to run machine learning stuff on the browser. Machine learning, you can use this GPU for that, because you can accelerate the matrix multiplication. And if you do that on the GPU, it's going to be way faster. And you can't really do that on WebGL because there are a lot of technical limitations. But WebGPU would basically enable that. Or if you want to build a video game with a lot of post-processing effect, and you need to fine-tune how the rendering process is working, then with WebGPU you can go the extra mile and get that 1% more. But in our cases, we figure out that for now it doesn't matter. When it will come out, maybe, but we will have to rewrite too much stuff.